Hello everyone, in this lecture we will be discussing about precision consideration in the case of MOSFET as switch. In this section we will show that these method of increasing the speed, as we have studied in the last lecture, that this speed can be increased by having a larger W by L, that is aspect ratio, or a smaller sampling capacitor, and these two parameters degrade the precision with which the signal is sampled. So let us see that the three mechanism in MOS transistor operation introduces error at the instant the switch turns off. Let us see them individually. The first parameter is channel charge injection. Okay, now consider the sampling circuit as shown in this figure 20, and recall that for a MOSFET switch to be on, a channel must exit at the oxide silicon interface, and assuming that V in is equals to V out, the total charge in the inversion layer as QCH is equals to W by L Cox VDD minus V in minus VTH, where this L denotes the effective channel length. When the switch turns off, this QH, that is the total charge in the inversion layer, exists through the source and drain terminal, and phenomena is called channel charge injection. Okay, the charge injected to the left side of figure 20 is absorbed by the input source, which creates no error. Okay, on the other hand, the charge injected to the right side is deposited on CH, which introduces an error in the voltage stored on the capacitor. For example, if half of the channel charge is injected onto CH, the resulting error will be equals to del V is equals to WL COX in brackets VDD minus V in minus VTH bracket closed upon 2CH. Now, illustrated in this figure 21, you can see over here that it is shown in the figure 21 that the error for an NMOS switch appear as a negative pedestal at the output. Note that the error is directly proportional to WL COX and inversely proportional to the capacitor, that is CH. Okay, so this is the effect of charge injection. Okay, now the fraction of charge that exists through the source and drain terminal is a relatively complex function of various parameters, such as the impedance seen at each terminal to the ground and the transition time of the clock. Okay, there is no rule of thumb that can predict the charge splitting in terms of such parameters. So how does this charge injection affect the precision? Let us see. Assuming that all of the charge is deposited on the capacitor, okay, and we have expressed the sampled output voltage as V out is equals to V in minus WLCOX in brackets VDD minus V in minus VTH bracket closed upon CH. Now, where the phase shift between the input and output is neglected, and thus we can rewrite it as V out is equals to V in brackets 1 plus WLCOX upon CH bracket closed minus WLCOX upon CH in brackets VDD minus VTH bracket closed. So this particular equation suggests that this particular output V out deviates from the ideal value to these two effects. Okay, a unity gain, this is the unity gain, which is equals to 1 plus WLCOX upon CH, and a constant offset voltage, which is equals to minus WLCOX VDD minus VTH upon CH. In other words, since we have assumed that channel charge is a linear function of the input voltage, the circuit exhibit only gain error and DC offsets. Okay, now it follows that the nonlinear dependence of VTH upon Vin introduces nonlinearity in the input-output characteristic. Or we can summarize, a channel charge injection contributes three types of errors and in MOS sampling circuit, and these are the gain error, the DC offset, and non-linearity, and this non-linearity cannot be tolerated at all. Okay, so this is simple input-output characteristic of a sampling circuit in presence of a charge injection. This is the ideal value, and it deviates from this due to the offset, due to the gain error, and due to the non-linearity. Okay, now the second parameters in precision consideration is clock feed through. In addition to channel charge injection, a MOS switch couples the clock transition to the sampling circuit capacitor through its gate drain or gate source overlap capacitor, and as shown in this figure 23, the effect introduces an error in the sampled output voltage. We can assume the overlap capacitance is constant, the error as del V is equals to VCK into WCOV upon WCOV plus CH. Okay, so as with charge injection, this COV is the overlap capacitance per unit width. And as with what we have discussed with charge injection, clock feed through leads to a trade-off between speed and precision as well. Okay, so this is the clock feed through. And the third parameters that affect this precision consideration is KT by C noise. Okay, as shown in figure 24, the on raised introduces thermal noise at the output. And when the switch is turned off, this noise is stored in the capacitor along with the instantaneous value of the input voltage. You can see over here in this figure 24, when the switch is off, this noise is stored in the capacitor with the instantaneous value of the input voltage, and it will lead to V plus Vn. Okay, so in order to achieve low noise, the sampling capacitor must be sufficiently large, thus which load other circuit and also degrades the speed. So these are the three parameters: the channel charge injection, the clock feed through, and KT by C noise, which we have taken while considering the precision of a MOS sampling circuit. Okay, if this is all in this lecture. In the next lecture, we will discuss about charge injection cancellation. Thank you.